Alright, so in the last video we talked about Rolle's theorem, and so uh, today's video I wanted to start with another idea, and that is, suppose I've got two cars. Their wheels are here, oops, kind of close together there, and they're on a racetrack, and the racetrack is just straight. Okay. And let's see, what are the cars going to do? The cars are going to leave at the same time, but then car A is always going to be, or I should say, the speed of car A is always bigger than the speed of car B. Car B. So velocity. Let's say, well, we can just say velocity. Velocity of A greater than velocity of B. Then what can you conclude? Then we can conclude that the position of A is always going to be bigger than the position of B, right? And this is known as the racetrack principle. The racetrack principle. And in fact, let's write this down in terms of two functions. So let f and g be differentiable, and f of a is equal to g of a. Further, let f prime of x be greater than g prime of x for all x in A to B. And in fact, you could put an equal sign here if you wanted to. And if we put the equal sign there, then what can we say about the position, the relative positions of f of x and g of x? F of x will be greater than or equal to g of x for all x in AB. Good. And so sometimes this is a nice thing to have. So just as a quick example, something I like to prove in my differential equations class is that prove that, whoops, sorry about that, I had a big flashing moment here in my video. Prove that for x greater than 1, natural log of x is going to be less than x. Now, geometrically, this is y equals x. Oops, jeez. That's not a very good x. Well, that's just pretend that's a line. And then my natural log function goes like that, right? And the idea is well, the question is which one is bigger? And it turns out that the line is actually bigger than the natural log for all x, right? And so the way we prove that is we start off by saying, well, we could start even here and say at this point where the natural log is 0, we have that our f of x is bigger than g of x, and then we compare derivatives. So at x equals 1, we have the natural log of 1 equals 0, and for f of x, this will be our f of x. I want that to be g of x. And let's make this f of x. And f of x equals 1. And so therefore, we have f of 1 is bigger than or equal to g of 1. Okay? So in fact, you could think of this as saying the car 1 is actually starting bigger than car 2 at the start of the race, right? Now, what happens to the derivatives? F prime of x equals 1, but g prime of x equals 1 over x. And so, which derivative is bigger? F prime is bigger. 1 is bigger than 1 over x for x greater than 1, right? By the way, that's not true if x is less than 1, right? So if x is 1/2, for example, then 1 is not bigger than 1 divided by 1/2, which is actually 2. Okay, but this works. And so therefore, because f of 1 started bigger than g of 1, and f prime is bigger than g prime for all x greater than 1, then we can conclude that x is bigger than the natural log of x for all x greater than 1. Good. All right, and by the way, it's pretty straightforward to see here that since the natural log between 0 and 1 is negative and x is positive, then therefore the line is bigger than the natural log for all x greater than 0 as well. Okay, but that's another issue. Good. So now I wanted to get to one more theorem today before we get to exercises, and that is actually the main theorem. And the main theorem for the day is the mean value theorem. And just as a side note, we now have the three value theorems of calculus after we get this one. It's the IVT, EVT, and MVT. Okay, so we'll come back to that. That's just kind of a side note that we do have another value theorem here today. Good. So before I start this, let's think about another little test, a mental test. Suppose that we start in Seattle at say 9 a.m. and we're driving to Walla Walla. We get to Walla Walla at say 2 p.m. Okay, and then the distance is about 300 miles. Okay, true or false? At some point in our travels, the velocity was exactly 60 miles per hour. Well, how far did we travel here? We traveled 300 miles, and how many hours are between 9 and 2 here? 3, 4, 5, this is 5 hours. 300 miles. And so if we think about that, 300 miles over 5 hours is a average of 60. And so suppose that we did not get to 60 miles an hour the whole time, right? That would mean that we could not have traveled 300 miles. Oops, sorry about that. Similarly, if we drove over 60 miles an hour the entire time, that means we'd have to travel more than 300 miles, right? And so we traveled exactly 300 miles in 5 hours, so therefore the idea here is that we want to show that at some point we were exactly 60 miles an hour. Good, and you can kind of see the reasoning for that, right? At some point your speedometer had to read exactly 60. Good. Okay, so let's see if we can prove that. This is actually the mean value theorem. The proof is actually using Rolle's theorem. Maybe before I prove it, I should state the problem formally. So here we go. I'm going to pause this while I write it down. Alright, so this is the statement of the mean value theorem, Let f of x be continuous on the closed interval from a to b, and let it be differentiable on the open interval from a to b. Then there is a c in the interval from a to b, such that f prime of c is equal to f of b minus f of a divided by b minus a. And by the way, you might notice that that is the average velocity, right, on the right hand side here. And that is what we computed up above. And so what you're saying here, kind of physics wise, is that on the left side we have the velocity, and on the right side you have the average velocity. And so what we're saying is that if you're going along, at some point your velocity has to be equal to your average velocity, your instantaneous velocity, right? Because you can't always be below your average velocity, because you wouldn't have gone as far as you did. And if you stayed above your average velocity, that means you would have gone further than what you did. So therefore, at some point, you have to be equal to your average velocity. Good. So why should this be true? I'm going to just prove this geometrically. We went through the proof of Rolle's theorem, and this actually uses Rolle's theorem. So let me just set it up, and then you can look at the book for the detailed proof. So the idea here is that you have a function from A to B, and your function goes from f of A to b f of B. It doesn't matter if it's above or below. You can draw it anywhere you want. We'll draw it above for now. Okay, and so your curve kind of goes through here like that. And so what we're saying here geometrically then is that the line here that I've drawn, that is not the function, this is the what am I trying to say? That is the secant line between AF of A and BF of B. And so what we're saying here is the slope of the secant line which is again f of B minus f of A. I'm trying to draw real small here. B minus A. That's equal to the derivative of at least one point C. Okay, so notice that that's not a zero. That's equal to this. These lines would be parallel. Okay, and so in this case, in my drawing here, I've actually got 3 points, 3 values of C for which the derivative is equal to 0. Now, how would I prove this? Well, the proof is pretty straightforward. The proof is actually just to take this graph and subtract the line that you see here, L of x, from your function f of x. And if you do that, your new function will look something like this. Whoops, I didn't give myself very much room there. This function is L of x minus f of x, which we'll call g of x. So if you take your line minus your function, you actually get a function that satisfies Rolle's theorem. And so the points now that give you a zero slope here are the same points above that give you the slope that's equal to your slope of your tangent line. Good, because you've kind of fixed the problem, right? So that we go from a generic f of x to a specific f of x that we can use Rolle's theorem on. Okay, I've gone over my time, and so in the next video we won't prove this, we'll just do examples. All right, see you then.